Everyone, I'm Kushag, and today we'll be looking for the basics of quantum mechanics. Okay, let us proceed forward. Let me just take up my laser pointer and let's begin with it. So, basics of quantum mechanics. Why quantum mechanics? So, classical mechanics that were Newton's mechanics and Maxwell's equation that were electromagnetic theory can explain macroscopic phenomena such as the motion of billiard balls or sockets, but they fail to explain us how particles at a quantum level, at a microscopic level work, because these laws have indeed proven to be wrong when it comes to a microscopic stage. In Newtonian mechanics, the laws are written in terms of particle trajectories. A particle is an invisible mass point object that has a variety of properties that can be measured, which we call observables. The observables specify the state of particle position and its momentum. System is a collection of particles which interact among themselves via internal forces and can also interact with the outside of world via external forces. The state of a system is a collection of the states of the particles that comprise of the system. Uh, All properties of a particle can be known to infinite precision. Trajectory, that is state descriptor of Newtonian physics. Evolution of the state, that is use Newtonian's second law. And principle of causality, that is two identical systems with the same initial conditions subject to the same measurement will yield the same result. Basics of quantum mechanics. So we have the wave particle duality that measures that quantum particles can act as both waves and particles. Quantum state is a conglomeration of several possible outcomes, measurement of physical properties. Quantum mechanics uses the language of probability theory that random chance. An observer cannot observe a microscopic system without altering some of its properties. Neither one can predict how the state of the system will change. Quantization of energy is yet another property of microscopic particles. So, basics of quantum mechanics, like we were talking about Heisenberg's uncertainty principle, that says that we cannot determine the momentum and the position of a particle altogether. That is what Heisenberg's uncertainty principle says. That is delta x of t naught multiplied by delta v x of t naught, that is greater or equal to 1 over 2 and h over 2 pi. Position and momentum are therefore considered as incompatible variables. The Heisenberg uncertainty principle strikes at the very heart of the classical physics, the particle trajectory. Okay, so yeah, the particle trajectory you see that describes that a particle that has variety of properties that can be measured. Means the position and momentum can be known, but Heisenberg's principle just proved it to be wrong. And we'll be focusing on how other classical laws were proven simply wrong by Heisenberg. So, the basics of quantum mechanics, the correspondence principle. When quantum physics is applied to microscopic systems, it must reduce to classical physics. Therefore, the non classical phenomena such as uncertainty and duality must become undetectable. Niels Bohr codified the requirement into his correspondence principle, that was 10 to the power negative 10 meters and 0.01 meters, atoms and molecules, etc. So, quantum mechanics focus over this pairs and classical physics for greater objects, which means that in very simple terms that quantum mechanics cannot be out there to solve the questions or solve any mysteries that is happening to objects that are quite large. And that is why these laws differ so much. And that's why Einstein tried to balance the general relativity that was the greatest piece of classical mechanics that we could ever get with quantum mechanics, but we were unable to do so. Yet we are unable to do so. We have not been able to prove it. Basics of quantum mechanics, particle wave duality. The behavior of a microscopic particle is very different from that of a classical particle. In some experiments, it resembles the behavior of a classical wave that is not localized in a space. In other experiments, it behaves as a classical particle that is localized in a space. So, the microscopic particle in space, so it's really weird. So, the corpuscular theories of light treat light as though it were composed of particles, but cannot explain the diffraction and interference. Maxwell's theory of electromagnetic radiation can explain these two phenomena, which was the reason why the corpuscular theory of light was abandoned. So, so this is what you've done yet. So Max Planck worked on black body radiation, in which he assumes that the molecules on the cavity walls described using a simple oscillator model can only exchange energy in quantized units. In 1905, Einstein proposed that the energy in an electromagnetic field is not spread out over a spherical wavefront, but instead is localized in individual clumps, quanta. Each quantum of frequency n travels through space with speed of light, carrying a discrete amount of energy and momentum photon used to explain the photoelectric effect, later to be confirmed by the X-ray experiments of Compton. This also awarded Einstein with the Nobel Prize in Physics. Particles as waves, double-slit experiment in which instead of using a light source, one uses the electron gun. The electrons are diffracted by the slit and then intervene in the region between the diaphragm and the detector, the Herr-Naven bomb effect. Well, you do not need to check it. Waves as particles. So we are only doing it till here. From the next class, we'll start with black body radiation. That is, we have everything advanced. Or should I just continue it? I think it would be better for continuing it. Or let's do it tomorrow. So this is to be scheduled as a thing that we'll be doing tomorrow. So thank you for watching. Kindly subscribe to me as well. Thank you so much.